In this video, we will continue our look at acid and base equilibrium. So we're going to start with sample exercise 16.10. What we're getting into now is looking at weak acids and bases, and when we calculate the dissociation of those, or when we look at the dissociation of those, we know that the acids are not going to fully dissociate. So if I look at this example here, I've got a 0.10 molar solution of formic acid. Formic acid is not one of our strong acids. It's not on the list. So we know that this is going to be a weak acid. So when this goes into solution, it will still dissociate into the hydrogen ion and the formate ion, but it's not going to fully dissociate like the strong acids that we were looking at previously. So this student prepared a solution of 0.10 molar formic acid and calculated the pH to be 2.38. And what we have to do is calculate Ka, which is our acid dissociation constant. So the first thing that we have to do when we are looking at these types of problems is we have to write our equation. So this is kind of the same as we were doing looking at the strong acids and bases. So we're going to write our equation. So we have the formic acid, and it's going to dissociate into the hydrogen ion and the formate ion here. Okay, so that's going to be our two products that we're going to have. So when we set up our acid dissociation constant, this is very similar to what we were looking at with our equilibrium constant, where our products are going to go on the top and our reactant here on the bottom. And just as a refresher, the brackets, of course, refer to concentration. So when we look at this formula here, in order to calculate Ka, we're going to have the concentration of the hydrogen ions, the concentration of the formate ions, and then the initial concentration of the formic acid. Well, we can get the concentration of our hydrogen ions because we have pH. We can work backwards, remember, to take the anti-log and get our hydrogen ion concentration from the pH. So that's what we've done here. So we know that pH is equal to the negative log of the hydrogen ion concentration, which we've been told is 2.38. So when we take the anti-log of that, we raise 10 to the negative power of pH, so the negative pH, and that gives us 4.2 times 10 to the negative 3. So that is our hydrogen ion concentration. So we've been able to now figure that out, okay? And we also know the initial concentration of the formic acid, but we don't know what the equilibrium concentration of that is. So we're going to have to go back to our ice tables that we learned in the last chapter. So remember, this ice refers to initial change equilibrium, and that is the concentration in molarity. So we'll plug in our reaction here. So we've got HCOOH, our formic acid, hydrogen ion here, and formate ion there. Okay, so from our problem, we know our initial concentration is 0.10 molar right? And we know that we haven't started yet, so our initial concentration of the hydrogen ion and the formate ion have to be 0. We figured out that the hydrogen ion concentration, we just calculated that, that's going to be 4.2 times 10 to the negative 3. So we calculated that, we know that now. And if that is the hydrogen ion concentration and it is one of our products, then it's also going to have to be the concentration of the formate ion. So I'll go ahead and put that in my table. So to get from 0 to 4.2 times 10 to the negative 3, we have to, add that. So just like we did last chapter, we're going to put that in. And I'll just go ahead and copy that for my hydrogen ion. All right, so if the hydrogen ion and the formate ion increase by that amount, then that means that the formic acid has to decrease by that amount, right? So our equilibrium then will be the initial minus the change. Let me just copy it. There we go. So that is what we're going to have to, figure out here. We don't know what that is going to be, so we've got to do a subtraction. Now, remember that weak acids do not dissociate completely. Well, when we're dealing with small amounts, then we can kind of do a little kind of hinky math here, as I like to call it. All right. So if we are looking at this number right here, 4.2 times 10 to the negative 3, that's a really tiny number. And if we subtract that from 0.10 and using two significant figures, then that's still going to give us 0.10. So this expression here, when we do that math, okay, is still going to give us a number, a result, that is, by all intents and purposes, using sig figs, the number that, it's still going to give us 0.10, right? So we don't have to subtract this out here. We can just stick with 0.10, okay? A small amount has dissociated, so we're just going to plug that in to our expression, okay? And so now we have it plugged into our expression. We have the equilibrium concentration of the hydrogen ion here, okay? And then we also bring down the formate ion here, and then we have our concentration of formic acid. And when we do the math, this is what we calculate for our Ka, our acid dissociation constant. Now, why was I able to use just this, what essentially was the initial concentration here? Well, because of the use of sig figs. And because this amount was less than 5% of the original concentration. Okay. If we were to approximate here and get an answer that is more than 5% of the original concentration, then we can't just do this assumption like we did here. Okay. But looking at this and knowing the amount was so small, we still end up with an appropriate value for Ka. As you do more of these, it'll kind of start to make sense with when can I just say, okay, well, this amount doesn't matter and I can just get rid of it and use the initial. And when does it matter? When do I have to actually use it? We're going to see an example here in just a minute where when you just do this assumption, it causes your amount to be greater than 5% of the initial concentration. Then we have to use the quadratic formula. You can use the quadratic formula on every single one of them, but it's tedious, it's cumbersome. You don't want to do more work than you have to. Okay. So now we've calculated our Ka. So the next exercise says from the hydrogen ion concentration obtained in sample exercise 16.10, calculate the percentage of formic acid that is ionized. Okay, so we have got our hydrogen ion concentration, and so now we can get percent ionization. So I just copied our hydrogen ion concentration from the previous problem, and we're going to plug that in to our percent ionization equation. This is the hydrogen ion concentration at equilibrium, which we calculated, and the initial concentration of our acid. Remember, we use HA to designate an acid. So we plug in our numbers here. We've got our hydrogen ion concentration. We've got our initial acid concentration, and then we multiply that by 100%. So the percent of formic acid that is ionized is 4.2%. Sorry, I forgot my percent sign there. So 4.2% of the formic acid is ionized. That tells us that it is a weak acid. Okay, remember, in a strong acid, 100% is ionized. So in this example, only 4.2% was ionized. Okay, let's move on now to sample exercise 16.12. So this time we have to calculate pH. So before we were given pH and asked to calculate Ka. This time we're going to be able to look up our Ka value, and we're going to use that to then calculate our pH. So I went to Appendix D in the back of the book, and I found my Ka right there. So now once I've got that, I can set up my equation. Remember, that's going to kind of be our first step for any of these, and then set up my formula for Ka, the acid dissociation constant. So here is my formula, all right, or my chemical equation. Here's my formula. So Ka is equal to concentration of hydrogen ion times the cyanide ion divided by the hydrocyanic acid. Okay, and that is equal to 4.9 times 10 to the negative 10, and we're going to use that information plus the molarity of the solution to give us pH. Okay, so let's get to our ice table. Okay, we're not going to be able to get away from these. So let me plug in the parts of my equation here. So the initial concentration, as I was given in the problem, was 0.20. So I'm going to plug that in here. Okay, and I know that my initial concentration for my products is 0. I don't know how much it's changed. Okay, I'm not able to calculate that at this point, but I just know that it's going to change. And when it changes, I'm going to end up with, some number of X, right? This is kind of what we did in the last chapter. You're like, wait a minute. I don't understand. When do I use X and when do I actually use a number? Okay, let me scroll back up. I was able to put an actual number here because I was given the pH and therefore I could calculate the hydrogen ion concentration. I don't have a pH in this one, so I can't calculate anything. I just know that it's going to be some number. So I'm going to add that number to 0, and it's going to give me my equilibrium concentration. And again, I'm going to change by some number so that here my equilibrium amount is going to be subtracted from my initial, which was 0.20. Okay. So I'm going to plug in this row into my equation. And that's what I have here. So I've got my hydrogen ion concentration, the cyanide ion concentration, and then my acid concentration there. And I know that that's equal to 4.9 times 10 to the negative 10. I looked that up in Appendix D. So that gives me x squared, because x times x is x squared. And this is another one of those examples where I can approximate, right? So I go from 0.20 minus x to just 0.20. So another example of where I can approximate, get rid of that x there. We can make the simplifying approximation that x, which is going to be the amount that dissociates, is so small compared to the initial concentration that it's not going to make a difference, just like we did in the earlier problem. So when I continue to kind of set this up, I'll cross multiply. X squared equals 0.20 times 4.9 times 10 to the negative 10. That gives me 0.98 times 10 to the negative 10. And then, of course, I take the square root of both sides. So I take the square root of x squared, gives me x. The square root of 0.98 times 10 to the negative 10 gives me 9.9 times 10 to the negative 6. Okay, I'm not done yet though. That is my hydrogen ion concentration, but we were asked to find pH. So then I plug that in to my pH equation, negative log of the hydrogen ion concentration. And remember, I'm going to take that to 2 decimals. pH always goes to 2 decimals. And that gives me 5.00 for my pH. Okay, so now we're going to move into one that's going to be a little bit different, where we aren't going to be able to use our simplifying assumption. So let's look at 16.13. So in 16.13, I have to calculate the calculate the pH and the percentage of HF molecules that are ionized in a 0.10 molar hydrofluoric acid solution. So first step, of course, is always going to be to write our equation. So here we have the hydrofluoric acid, and it will ionize or dissociate into the hydrogen ions and fluoride ions. Now, just like before, we're going to have our ice table here. So let's plug in everything. So I know from the problem, my initial concentration of HF is 0.10, and both my hydrogen and my fluoride are 0. And just like in the last one, I have no information other than I know that it's going to change by some number. So we'll plug that in. And I know that this will subtract by that number, and I will have 0.10 minus x. All right, so there's my ice table. I've got it filled in. And I can go ahead and set up my Ka expression. I know that it's my products over my reactant. I pull the x and the 0.10 minus x, and I found this in Appendix D. So I just went to Appendix D, looked up the Ka for hydrofluoric acid, and there it is. Okay, so I've got basically the same equation that I had in my last problem. Right there. All right. So what makes this problem different? Well, when we just solve it just as it is, we get 8.2 times 10 to the negative 3. Okay, so if we just get rid of the x right here, like we've done before, and we solve it just straight up, we get 8.2 times 10 to the negative 3 molar. However, this amount, this approximation that we've got here, it's greater than 5% of our original concentration. So that tells us that it is a significant amount, and we're going to have to work the problem in standard quadratic form. So if you simplify, so this is one of those general rules that we get into. If x ends up being more than 5% of the initial concentration value, it is better to use the quadratic formula. So we need to plug in the quadratic formula. Okay? So let's get in there. The first thing we've got to do is set it up in our normal quadratic form. Okay, so what I have to do is cross multiply. So I get x squared up here, and that's going to be equal to 6.8 times 10 to the negative 4 times this quantity here of 0.10 minus x. So that's what I've got here. Well, then I do the full method like we talked about last time, okay, where you have to multiply first outer, inner last, okay, and we end up with this expression, and when we put it in standard form and set it equal to 0, this is what we have. Okay, so x squared plus the quantity of 6.8 times 10 to the negative 4x minus 6.8 times 10 to the negative 5 equals 0. Once we have it set up in that form, then we can plug it in to our quadratic formula. And as a refresher, quadratic formula is negative b. So remember, these are terms. We have a here, b, c. So I have negative b plus or minus the square root of b squared minus 4 times a times C. Well, A is 1, so we don't have to put that in there. And that whole quantity is over 2 times A. Again, A is 1, so it'll just be over 2. Okay, so we will run through the gamut here and solve it. Well, since we've got that plus minus in there, we end up with two solutions. 7.9 times 10 to the negative 3 and negative 8.6 times 10 to the negative 2. Well, we can't have a negative concentration. Remember, that's what we're trying to deal with here. So this is an unusable solution. So we're going to go with this. X is equal to 7.9 times 10 to the negative 3. Now remember, X is our hydrogen ion concentration. And we need that to determine pH. So once I get X, I know that that's equal to my hydrogen ion concentration, which is the same as my fluoride ion concentration. And when I plug that in, I can finally calculate pH to be 2.10. Now, they also asked us to determine the percent ionization. That's the concentration that's ionized over the original times 100. So here's what I calculated. This is what percent was ionized. This was my original concentration. And so this is my percent ionization, 7.9%. Now, if we had kept our assumption back up here, okay, then we would have come up with 8.2%, and we would have come up with a completely different pH. So that's why we have to look at those approximations. If it's greater than 5% of the original concentration, you've got to use quadratic formula. Because as you can see, it will affect. Our approximation got us 8.2 times 10 to the negative 3. Our real answer was 7.9 times 10 to the negative 3. So, yeah, that's not a huge difference, but it's enough of a difference to make the pH different and our percent ionization different. So you have to be more correct. All right. Okay. Moving right along. Our next exercise is still looking at the section on weak acids. But this time we're looking at what we refer to as a polyprotic acid, which is when we can have more than one ionization. So we can have two successive ionizations. And when we look at this problem, 16.14, we're looking at the solubility of carbon dioxide in water in this carbonic acid reaction here. Now, carbonic acid, which is H2CO3, it is a diprotic acid, which means it has two acid dissociation constants. It goes through two successive ionizations. Okay, it goes from H2CO3 to HCO3 minus, and then finally into CO2. Now, when we have more than one ionization, we have two acid dissociation constants, Ka1 and Ka2. And these are found in table 16.3 in your book, or you can find those values also in Appendix D. When we look at Ka1 and Ka2 for carbonic acid, Ka1 is 4.3 times 10 to the negative 7. So let me just kind of make a little note here. So let's see. So Ka1 is 4.3 times 10 to the negative 7. And then we also have a Ka2 value, that second dissociation constant. So Ka2 is equal to 5.6 times 10 to the negative 11. Some acids even have 3, but we're not going to worry about any of those for our purposes now. So there are our two acid dissociation constants. If the two Ka values differ by more than a factor of 10 to the third, then we can calculate the pH by looking only at our first acid dissociation constant. So when you have an acid that has two acid dissociation constant values, like we do here, look at the power, look at the exponent on the 10. If it's greater than a 10 to the 3 power difference, then you don't have to worry about this one. You only have to look at the first one. Okay, and that's going to make solving the problem a lot easier when you only have to consider one acid dissociation constant. Okay, so we are given the pH and the molarity, and we need to, we are given the molarity, and we need to calculate the pH. We've already looked up our Ka value here, and we know we're going to use Ka1. So, and this time I've already got the equation given for me, so I'm going to plug that in. Now, or I've already got one equation given for me. And so I've got to look at that and say, ooh, that's not my dissociation equation. So don't make the mistake of just saying, oh, I'm just going to go right with this. We still have to get our correct equation first. And I haven't put that in here yet. So I'm going to start with my acid, which is H2CO3. So that's going to be first. And I know that that's going to dissociate into the hydrogen ion and carbonate. Sorry, that's not carbonate. My carbonous acid. So here is my acid, and this is what it's going to dissociate into. All right. I've been given my initial concentration right here, so I'm going to go ahead and plug that in. I know that these are both 0, and I know they're going to change by some number x, and that's going to decrease by x. So let's get that. All right. So now I've got my ice table all filled in here. And then I need to get my equilibrium constant. Okay, I've switched over here to a different screen to now go through this with you. So here is the ice box that we set up. And here is my equilibrium constant expression. Remember, my products go on the top and my reactant goes on the bottom. So I set that up, and I'm going to solve for x. And once I solve for x, this is what I get. Okay, so x is equal to 4.0 times 10 to the negative 5. Since this is not greater than 5% of my initial concentration, I can make my simplifying approximation. So I can just say that my, get rid of my x there in the change from my initial concentration. And so then I can set this up to solve. And once I solve, so remember that's going to be x squared, and I cross multiply 4.3 times 10 to the negative 7 times 0.0037, and I get 1.6 times 10 to the negative 9. I'll take the square root of that and get 4.0 times 10 to the negative 5. And remember, x is our hydrogen ion concentration, and then we can plug that into our pH formula, and we get 4.40. So again, that's what we're trying to solve, is our pH. So why was this one different than the last one? Well, number one, we had to consider the fact that we had two acid dissociation constants for the acid. But remember, we look, is it greater than a factor? Are they greater by a factor of 3 or different by a factor of 3? If they are, we only consider the first one. And then when we looked at our number here, the Ka1 was so small that it wasn't more than 5%, or when I calculated it wasn't more than 5% of my initial concentration, so I could simplify and I didn't have to go through the quadratic formula. All right, so that is 16.14. Now we can, or we're going to switch gears and look at weak bases. And we can calculate our base dissociation constant in much the same way that we do our acid. So now we're going to look at sample exercise 16.15. I know this says 16.13, but this is a different version of the book than we use. So, but it's the same problem. So what we're asked now is to use Kb, which is our base dissociation constant, to calculate the hydroxide concentration and pH. So because we're dealing with bases now, we are going to look at hydroxide concentrations instead of hydrogen ion concentrations. So we have a 0.15 molar solution of NH3, and we need to calculate hydroxide concentration and pH. So first things first, we have to get our ionization reaction. So we're going to start with the base that we were given, NH3. Now, with these calculations, you'll notice we've added something here that we did not have with our acids. We have water as a reactant. So when you are working on your equations here, or your chemical equations, the reactions, don't forget you need to add water as a reactant, because that's what's going to allow the formation of our conjugate acid and the hydroxide there. Okay. Now, when you plug in your expression to calculate the, or to have the base dissociation constant, water is not a part of it. Remember, last chapter, we said that when you have these types of equations, pure liquids and pure solids are not part of them. So water is part of the reaction, but it is not part of the expression. So we put our products on top, reactant on bottom, and I look up in my table, Appendix D, or Table 16.4, and that gives us our base dissociation constants, and for NH3, ammonia, it is 1.8 times 10 to the negative 5. Okay, so then we move forward. We are going to get our ice box here. Okay, now you'll notice we've got 4 columns in our ice box now. This one right here corresponds to water. It's not a part of the expression, so we don't consider anything with it in the ice box. And to be truthful, when I work these types of problems, I don't even include it in my ice box because it's not going to matter. It's not a part of the expression. Okay? So you can just leave it off completely if you want to. So we have our initial concentrations, 0.15 molar for the ammonia, 0 for our 2 products. We know that they're going to change by a factor of X. And so here's our equilibrium concentration here. And when we plug that in, here is where we are. X times X over 0.15 minus X. And we already know our Kb value, 1.8 times 10 to the negative 5. Okay, so we set that up. And just like before, we have to look at the number here. Kb is so small that the amount of ammonia that's going to react with water is so much smaller than that, we can do our simplifying assumption. All right. So again, this is something you need to pay attention to. But if that number is really, really tiny, then you can just forget about it here. So once we solve for X, so once we get this in our equation, do our cross multiplication and solve for X, X is equal to 1.6 times 10 to the negative 3. And remember, X in this case is our products, and one of those that we're trying to figure out here is the hydroxide ion concentration. So now we've done that. Okay, it is 1.6 times 10 to the negative 3. But they also wanted to know, well, we're just looking at Kb. We don't have to do pH in this one. So we have solved for the hydroxide ion concentration. Now, in this textbook, they ask you to determine pH. Well, we can just go ahead and do that. We know that pOH is the negative log of the hydrogen ion concentration. So we go ahead, plug that in. We end up with pOH of 2.80. And from our earlier calculations, we can get pH by subtracting from 14. So our pH here is 11.20. So that is... Moving right along, we get to sample exercise 16.16, page 698 in your textbook, where we can use pH to determine the concentration of a salt. So, in this problem, we have a solution that we made by adding solid sodium hypochlorite. And we added this to water, and it has a pH of 10.50. And so we have a reaction that's given for us, and we're going to look for our base dissociation constant Kb. We need to figure out how many moles, what is the number of moles of that sodium hypochlorite that were added to the water. So we're going to take our pH and we're going to determine how much of this substance, this sodium hypochlorite, was actually added to the water. All right. Now, sodium hypochlorite is an ionic compound. It is a salt that consists of the sodium ions and the hypochlorite ion. It's a strong electrolyte. It completely dissociates into, in solution, into the sodium and then to the chloride ion, which is a weak base. Now, when we look this up, and let me go up just a bit. I think we can find, where's that equation? There it is, right there. So here's the equation for this. Once it is dissolved in water, it acts as a weak base, this hypochlorite ion. And as such, it has a Kb value of 3.3 times 10 to the negative 7. So using this information, we can calculate how much of that salt was added to water. So let's first calculate the OH, the hydroxide ion concentration first. So we know that the pH is 10.5. So we can use that to use the anti-log and get our hydroxide ion concentration. So that's what we've done here. So we said POH is equal to 14 minus the pH, which was given in the problem as 10.50. So our POH is 3.50. Take the anti-log, 10 to the negative 3.50 power, and here is our hydroxide ion concentration right here. All right, so now we've got a concentration. We're going to go to our ice table. And again, this one, because it's a base, has water in it. Ignore it. It doesn't amount to anything. We just need it for our expression here, but it doesn't go in our ice table, or it doesn't make a difference in our ice table. So this time, we actually have something to plug in. We don't know our initial concentration here, but we do know the hydroxide ion concentration right here. We just calculated it. So we can plug it in here. And we know that the hydroxide ion concentration and hypochlorous concentration are going to be the same. They're both on the product side here. Okay, so they're both the same. We know that the initial concentration of those, since their products, is 0, and here's the factor by which they change. So then we don't know our initial concentration. That's what we got to figure out. But we know that the change is going to be minus 3.2 times 10 to the negative 4. So here is our equilibrium concentration for the hypochlorite ion. Okay, so that's what we've got to figure out. That's our weak base. That's what we're trying to figure out. So we set up our expression just like we have before. And this time I'm not going to have the x squared on top because I have a value for that. So I'm going to plug that in. I already know Kb, that's a constant. I've looked that up. I know what that is. Okay. And now I cross multiply and I solve for x. And x is going to be 0.31 molar. So that is my initial concentration. Okay. So now that's what I was trying to solve. I mean, that was my initial concentration of the chloride ions. Well, we can now figure out how many moles of the sodium hypochlorite were added. So some of those chloride ions did react with water. I mean, they had to, but it's very few. So we're going to say that the solution is 0.31 molar, even though some of those have reacted with water. Because the solution is 0.31 molar and the total volume is 2 liters, then we have to multiply by 2. Remember, molar, the M there, is moles per liter. So we have 0.31 moles in 1 liter, but the problem told us that we had made 2 liters. So we have to multiply by 2. So our answer is 0.62 moles. That's how much moles we added to get 2 liters of the solution. So make sure you don't skip that final step. If you're given any amount other than 1, you've got to multiply your molar concentration by the amount of water. Okay, so if it's less than 1 or greater than 1, you've got to multiply that molar concentration by the amount. All right, so that was 16.16. Now the rest of this unit gets into the relationship between Ka and Kb. So we can look at the calculation for Ka or Kb if we have a conjugate. So in your book, this is sample exercise 16.17 on page 701. And we're asked to calculate Kb for the fluoride ion and Ka for the ammonium ion. So we have to kind of figure out then what are these dissociation constants. Now the fluoride ion is the, we're going to use the acid dissociation constant of HF for that. And then for the ammonium ion, we're going to use the base dissociation constant of ammonia. Now, we can use our ion product constant of water, remember Kw, we looked at that in the last video. We can use that to help us find Ka and Kb values for conjugate acid-base pairs. The product of Ka and Kb is equal to Kw. Okay, so Ka times Kb is equal to Kw only for conjugate acid-base pairs. We can't use this for any other relationship, only for the conjugate pairs. So let's take a look at this. So when we go to Appendix D to look at HF, we find that Ka is equal to 6.8 times 10 to the negative 4. So then we plug this in to our equation, Ka times Kb equals Kw. Well, solving for Kb gives us Kw, which is always 1.0 times 10 to the negative 14 at 25 degrees Celsius, and we divide that by our Ka, which is 6.8 times 10 to the negative 4. Solving for that gives us 1.5 times 10 to the negative 11. And so that is our Kb for the fluoride ion, which is the conjugate base for HF. Then we do the same thing for the second part of this. We're going to look at Appendix D, look at our Kb value for NH3 ammonia, which is a weak base, and that is equal to 1.8 times 10 to the negative 5. So this time, we're going to solve for the Ka, for the conjugate acid, which is ammonium, NH4 plus. So Ka is equal to Kw divided by Kb, and we get 5.6 times 10 to the negative 10. So again, this is a pretty easy calculation. You just remember Ka times Kb equals Kw. But you have to remember that it is only for conjugate acid-base pairs. You can't use it. Our next section gets into looking at salt solutions. We already kind of took a little bit of a look at this when we did the problem with the sodium hypochlorite. But now we're going to look at how we can determine if a salt solution is going to be acidic, basic, or neutral. So in your book on page 704, you will find 4 rules or 4 combinations to help you determine if a salt solution is acidic, basic, or neutral. And this is exercise 16.18, also on page 704 in your book. So the first salt that we have is barium acetate. Okay, so BaCH3COO2 is barium acetate. So we're going to look at the rules there and just determine from those if the salt is acidic, basic, or neutral. So once we put this salt into a solution, it will dissolve into barium ions and acetate ions. So barium is a heavy alkaline earth metal. Now, based on our rules, it's not going to react with water, so it's not going to affect the pH. The anion, which is the acetate ion, it is the conjugate base of a weak acid, acetic acid. And it will hydrolyze to produce hydroxide ions, which will make the solution basic. And this is combination number 2, which tells us if the salt contains an anion that reacts with water to produce hydroxide ions, which is the acetate, and a cation that does not react with water, which is the heavy alkaline earth metal barium, we expect the pH to be basic. And it says such is the case when the anion is the conjugate base of a weak acid and the cation is from group 1A or one of the heavier members of group 2. And barium is one of those. Okay, so A would be basic. All right, our next one is ammonium chloride. So when they dissociate, we'll have ammonium ions and chloride ions. So ammonium is the conjugate acid of a weak base, ammonia, and so it's acidic. The chloride ion is the conjugate base of a strong acid, and so it would have no influence on the pH. Because the solution contains an ion that's acidic, which is the ammonium, and then the chloride that has no influence, it will be acidic, which is rule number 3. In the next one, we have kind of a complicated one here. We've got CH3NH3Br. CH3NH3 plus is the conjugate acid of a weak base, which is CH3NH2 and amine. And we looked at these amines when we were talking about weak bases. So it's acidic. The Br is a conjugate base of a strong acid, which is HBr, and so it would be pH neutral. And So this one is also going to be acidic because of the CH3NH3. KNO3, potassium nitrate. So we'll have dissociation into the potassium ion, which is a cation in group 1, and the nitrate ion, which is the conjugate base of nitric acid, which is considered one of our strong acids. So neither one of those is going to react with water, so this would be neutral. And then that is combination number 1, or rule number 1. And then our final one that we have there, AlClO43, will contain aluminum ions and the perchlorate ions. Cations such as aluminum that have a charge of 3+ or higher are considered to be acidic. So anything that has a 3+ charge or higher will be acidic. And then the perchlorate ion is the conjugate base of perchloric acid, which is a strong acid, so it's not going to affect the pH. So this solution will be acidic due to the... Hopefully this has helped you understand some of these more complex equations dealing with acid-base equilibria. And as always, if you have any questions, please feel free